Yesterday we have learned the one of the question that would be teach us that how to do the Huffman coding, and we have taken one example, but due to the lack of the time we have not completed it. So I hope up to this point all of you have noted the problem and their solution also. Now we would be proceed. We have already made a Huffman tree yesterday. Now today what we would do, we will be just trace back it for the x6 and x7 up to x5. We have already done the tracing. Now we have to be do it for the x6 and x7. So if we would be see x6 as it would be 0.02, and if you have to be go here, then 0.03, then 0.006 actually, and then again this is the path, and lastly 0.5. Actually it is a reverse tracing, but as per your convenience during the practice you can either go to the front tracing or back tracing. So we have to be count the bits but at the reverse order. So 0 would be at the MSB, then it is 1, then 0, then 0, then 0, then again 0. So 0, 1, 4 times 0. Okay. Similarly, for the x7, we can also do the same. So you would find that all the tracing it would be same, only the last branch when it would be changed, and this is the section where it would be changed. So it would be what? 0, 1, 0, 0, 0. 3 times 0 would be common. Only of this 0 there is a 1. So it would be 1. So this is the way that we can uh, after using the backtracing method, we can encode the symbols given here using the Huffman coding. And after tracing this, you have to just uh, write down the values in your table. So I have written here. So you can see for the first one it is a 1, then 0, 0, then 0, 1, 1, then 0, 1, 0, x5, 0, 1, 0, 0, 1, and xx and x7 we have done today. And the code word length is also written in front of this, as well as I have find out the self information that you can also do. For our university paper, it is optional, you can take, but if you would be find out this, it would be give you the better marks. Okay. Now we have to find out the entropy. So we have know that what is the formula of entropy, that is Hx is equal to minus sigma. You can take a k or j, whatever the variable you want to take, and that is 1 to 7 because there are the 7 symbols are there. Put up the value of entropy here as well as the value of probability, like like the probability is here 0.46 and this is also log base to 0.46. Like this, we have to be go for the 7 symbols. I am not going to the description because already we have done lots of the problem on this. So I would be going to directly write the value of the entropy 1.9781 bits per message. Okay. Similarly, we can also find out the average code word length here by using this formula. Now you have to just put a 0.46 into 1, then 0.30 into 2, like that. You have to be according to the code word length and their probability. You can find out the average code word length, and that would be come here 1.99 bits per message. Now you have to be put up in the efficiency formula. you would be find out 1.97 upon 1.99. For percentage, you can multiply with the 100. So you would be get the value 99.40%. Okay. So this is the efficiency of the coding that we have done using the one of the method using the Huffman coding. Now, same coding we have to perform with the help of the second method according to Huffman coding. So when you have to go for the second method, it is again a very simple way that you can perform this. So for this, I have already written the messages for the second method. We have to start from the bottom one as usual. Just assign this 0 and 1 and summation of this two probability 0.03. But here we are keeping the summation where it is coming the same value of the next upcoming probability. So we will be keeping it on the label below that next probability like this. So 0.03 is same as the next probability, that is 0.03. Okay, but we have not changed its level. So the summation value would be keep it below, and then we have to perform 0 and 1 like this. Then again do the summation. It would be 0.06 would be came, and again we would be write it below the next probability. Next probability is 0.06. So this summation would become below of that. And then again we have to perform the same procedure, 0 and 1. Okay. Now after doing this, again we have to go for the next symbol. So you have to do the summation. It would become 0.12. That is again similar to the next value of probability, 0.12. Assign 0 and 1, and here and then again do this same procedure, and this summation would be already coming less than 0.3. So it is by default it would be below that 0.30. Okay, it is because it is less than this, so there is no need of deciding or selection is there required. It is already less than, so it would be keep it below and do this same procedure. Now the summation of these two would be greater than the next value. So as per the general rule, we have to keep it above, because always when the probability is summation of the probability would be if more than the next value probabilities, it would be keep above. Only we have to take the decision for the same value of probability. In the last method, what I have done, the summation of probability has kept above the next value of probability if both values coming same, and here I have kept it below. Now we have to be using this method. We have to do the function of the reverse tracing and writing the value of the code words for the corresponding symbols. For x1, you can see this is the straight line. This is binary 1. For x2, you can come here up to this, and then we have to moved. So it would be 0, 0, and then for the x3, you can see here for x3 from this point we have to come here 0.24. Then again this is a straight line. This would be 0, then 1, and then 0. 0, 1, 0. This would be the answer for x3. Simultaneously, you have also do this, noted down all the values that I am done here. Okay. Now we have to become for the next, that is x4. Again come to this point, 0.54, then this is the value. Yeah. Now this is very simple for tracing because we have kept it below. So it would be 0, 1, 1, 0. Okay. Then again we have to go for the same method of x5. So we have to see the value 0, then 1, then 1, and then 1, and then 0. So what would be there? 0, 1, 1, 1, 0. Okay. So this is up to the x5. For similarly, we can apply this for x6. So what is the value of x6? If you have to be see that, we start from this point, then 1, 1, 1, and 1. So up to this point, 0, 1, 1, 1, 1, and then finally goes to 0, to 0 for x6. So x7, it will be also having the same value 0, 1, 1, 1, 1, and last one is just diverted here. So again 1. So this is the way that you can do the reverse tracing and find out the corresponding codes for the measure symbols. So I am going to write this on the table that we have taken. Now here the x1 is 1, x2 is 0, 0, 0, x3 is 0, 1, 0, x4 is what? 0, 3 times 1, 0, then x3 is what? 0, 1, 0, and x4 is, this is not here, 0, 1, 1, 0. Okay, and then x5 is 0, 3 times 1 and 0, x6 is 0, 4 times 1, 0, and x7 is 0, 5 times 1. Okay, so in this way you can write the length 1, then 2, then 3, 4, 5, and then 6 and 6, and you can calculate the self information by your own. That would become same as in the previous case. Okay, after doing this we have to find out the entropy. Entropy would be, actually do not need to recalculate entropy, it would be came as same that we have find out in the previous uh, slide, that is 1.9781, because entropy does not change, it would be having the same formula. So I'm just writing here the value of h of x, that is equal to 1.9781 bits per message. Okay, now after that we have to find out the L. L could be changed. So as per the formula of L, that would be, you have to be write the value of probability and their code word length, and just do this, you would be get the value 1.99 bits per message. And entropy efficiency would be now 1.9781 upon 1.99 into 100, you would be get the efficiency would be 99.40%. So can anyone tell me what the difference between the two different methods and their value of efficiency? Can anyone tell me from your class? What you have observed? In the first case, we have the efficiency 99.40, and In the second case also it is having the 99.40. So it would be give you a conclusion, that is the Huffman. This is very important statement you have to be right after the solution. The Huffman codes are not unique for a given set of probabilities. This is very important comment after finding out the value of efficiency. Okay. So in this way, we can say that Huffman codes are not unique. So you can solve the Huffman coding based problems in multiple ways. Okay. Now we have to be end the unit number 3 on this point and move to the next unit, that is unit number 4. Okay. So unit number 4 is basically based on baseband signal encoding. Baseband signal encoding. So unit number 4 would be based on this topic. Unit number 5 would be on the band pass signal encoding, that we have now entered into the actual modulation. So these are the some outlines for your unit number 4, that we have to be go through the topics like block diagram of digital communication system, digital versus analog sampling process. We would be already learned the sampling process in the analog communication. Again, we have to be just revisit the concepts. Then PCM generation, pulse code modulation generation and reconstruction, quantization noise. These all I think you have already covered in the analog. It will be just a exploration of the concept. Then we have to learn delta modulation, adaptive delta modulation, DPCM. Then finally basic line codes that we have already implemented on the practical as well. So this is the topics we are going to learn in the unit number 4. So start with the topic block diagram of digital communication system. So everyone note down this diagram, that is a block diagram of digital communication system that I have taken. So you can see here the important element for this digital communication system. This is the source where the information would be generated. Okay. And then it would be, source could be any human being, whatever I am talking, that is also one of the source information. So this would be further passed through a source encoder, where we have to be encode the messages. So in the unit number 3, we have focused on this source encoding methods like Shannon-Fano coding, Huffman coding. These all are the source encoding methods that we have learned. And then it is passed through the channel encoder that already we have covered in the unit number 2, like block coding, convolutional coding, that all are the part of the channel encoder. After this, where your information would be converted into digital and encoded and encrypted, that it would be sent to the modulator section, where for the transmission purpose, again this digital information would be reconverted into the analog equivalent, because in the propagating media, either it is a wired or wireless, information would be transmitted in the form of analog form. So it would be again converted into analog form by the use of some technique, modulation technique like ASK, PSK, FSK. And then finally here it would be the transmitter section would be end, and from the transmitter antenna it would be propagate on the transmission media, and then the information would be, or message would be entered into the channel, where maybe some noise or some errors would be added, and finally it would be received by the noisy signal would be received by the receiving antenna, receiver antenna. And at that end, again the demodulation, the reverse process of the modulator would be there, and then after demodulation of the message, it would be passed to the channel decoder, where it would be decrypted, and then again it would be passed to the source decoder, that it would be whatever the redundant bits has been removed, and then finally the original information or equivalent to the original information would be reached to the destination, or whatever the user is there, he would be received there. So in this way, this all process is going on. We have already gone through this, and it would be in the 5th number unit, it would be in detail, and in between of that we have to be unit number 4 also, baseband transfer that going to learn. Okay, now I would be just this is, I hope up to you have this point, you have just drawn this diagram. Now we will become to in detail description of these blocks. Okay, this is the theoretical point, so you could be asked a question on that, so you have to be describe it in descriptive manner. So in this above digital communication block diagram, there is a 3 basic signal processing operations has been identified. You can already identify this. First one is the source coding, channel coding, second one, and third one is the modulation. So you can assume that the source of information is digital by nature, or maybe converted it into the digital form by some electronic circuitry. So the first signal processing operation, that is signal encoding or signal coding, in that source encoders maps the digital signals generated at the source output into the another signal in digital form, and this mapping is 1-to-1. This mapping is 1-to-1, and the objective of this mapping is to eliminate the redundancy or reduce the redundancy, so as to provide an efficient representation of the source output. So in the source encoding, we have to eliminate this redundancy. This is very important. Since the source encoder mapping is 1-to-1, and the source decoder simply perform the inverse mapping. So in the receiver section, there is a last block was source decoder. So it would be just perform the inverse mapping or inverse operation of the source encoder, and thereby it would be delivered to the users at the receiving end. That is a signal, that is a reproduction of the original digital signal. So what is the benefit of this? The primary benefit of this application is of source encoding is it would be reduce the bandwidth requirement. Why it is reduce the bandwidth requirement? Because we have reduces the or eliminated the redundancy in the message. Now if you have to come to the second signal processing block, that is channel coding. So in the channel coding, what is the objective? The objective of the channel coding is for the encoder to map the incoming digital signal into a channel input, and for the decoder to map the channel output into output digital signal in such a way that the effect of channel noise is minimized. This is the main purpose of channel coding. We have to be optimize the signal. It means the effect of the channel noise should be minimized. That's why we have to be perform certain coding methods in the channel. And for that purpose, we would be add a redundant bits. In the source coding, we are not using redundancy, but in the channel coding, we use the redundancy. Okay. Now, further in the channel coding, you have to see that for minimizing the noise that I have already told you, we have to be introduce the redundancy. In the channel encoder and exploiting it in the decoder also to reconstruct the original encoder input as accurate as possible. Thus, in this way, we can say that in source coding, we remove redundancy, whereas in the channel coding, we introduce controlled redundancy. So from above discussion, it is clear that we may perform source coding alone and channel coding alone, or maybe both together. But if you are going to implement a channel coding and source coding on a same together, so in that case, what happens? Source encoding would be performed first and channel encoding would be after that in the transmitter section. And at the receiver section, channel decoding is first and source decoding at the last. So this is the sequence of operation. So you can also see from this block diagram that in the transmitter section, source encoder is applied first and then channel encoder. But in the receiver section, if you have to be see, the channel decoding is first and then source decoding. Here you can see that we are adding the redundant bit, and here we have removed this redundant bit. Okay. So in the receiver, we have performed the reverse order that I have already told you. But when we have to be use source encoder and channel encoder as a combination, so it would be increase the circuit complexity, but our system performance would be improved. So one of the drawback is it would be increase the circuit complexity, but on the other hand, we have got the benefit of better system performance. Now, apart from this section, to this section, we have to go to the third one, that is modulation. So in the modulation, if you have to be see, it is performed with the purpose of providing for efficient transmission of signal over the channel. So how can we would we perform the efficient transmission? By using the means of modulation techniques. So in this particularly, the modulator operates by keying shifts in amplitude, frequency, and phase of a sinusoidal carrier wave that is coming out from the channel encoder output. So whatever the channel encoder output signal would be there, we have to be modulate it by means of changing its amplitude, frequency, or phase by applying a sinusoidal carrier. Okay. Now we can see that the digital modulation technique for doing so is referred to as amplitude shift keying, frequency shift keying, or phase shift keying respectively. So a detector performs demodulation and thereby producing a signal that follows the time variation in the channel encoder output. And the combination of modulation, channel, and detector is called discrete channel. The combination of what? Modulator, channel and detector is called as a discrete channel. Why it is called a discrete channel? Because both input and output signals are in the discrete form. Now we have to be just explain the block diagram of the digital communication system one by one block. So what happens that traditionally coding and modulation are performed as separate operations, and introduction of the redundant symbols by the channel encoders appears to increase the transmission bandwidth. Obviously, when you have to be introduce the redundant bits on your message, it would be increase the transmission bandwidth. But in some application, these two operation means coding and modulation are performed as one function also, and in such case, transmission bandwidth need not to be increased. So both way is possible. So in such situations of this kind, when we have to be perform the coding and the modulation in a one function or joint function, so it would be imposed the distinct pattern on the transmitted signal, which are discernible by the combined action of channel decoder and detector in the receiver section. So this is all about the description of block diagram of the digital communication system. Okay. In the analog communication, it is very simple block diagram, less amount of blocks are there. But in the digital communication system, we have seen that we have to be required a source encoder, channel encoder, along with the modulation. Now we have to move to the second topic of this particular unit, that is digital versus analog sampling. So here basically we have to be learn the sampling theorem, how we have to be convert the analog signal into the digital form. Okay. So if you have remember the sampling theorem is basically for band limited signals of finite energy. So the sampling theorem, it would be strictly band limited signals of finite energy. You can define it in the, or there is a two statements basically. The first one is the band limited signal of finite energy that has no frequency component higher than W hertz is completely described by specifying the values of signal stands of the time separated by 1/2 W seconds. So what is the first statement? A band limited signal that is having the finite energy. Of this signal, there is no frequency component of that particular band limited signal should be higher than the W hertz. That is the fundamental frequency of that signal. And if you have to be represented in the time domain, it should be represented if signal component would be separated by the 1/2 W seconds, or you can say T by 2 seconds. 1/W is the T time period of the signal. Here I have used the frequency as a W, not the F or FS like this. FM or FS. There's a various books are there. I have just following the digital communication by the Simon Hacking. So I have used the notations used by that particular author. In some books also you can see that it is W, instead of W you can use a FM, maximum frequency. Okay. And what was the second statement? The first statement is that valid for the transmission of the signal, and second statement is for the receiving of the signal. A band limited signal of the finite energy that has no frequency component higher than the W hertz is completely recovered from a knowledge of its samples taken at a rate of twice of W samples per second. So this is very important relationship that is also defined by the Nyquist criteria. So it could be, the sample could be, from the knowledge of sample you can recover the actual signal. If it would be satisfy this Nyquist criteria, the rate of sampling should be either equal to or greater than twice of fundamental frequency W. Okay. Now you can enter your attendance on the chat box. There is a very less amount of time is remaining, 3 minutes. Okay. So these are the two statements of the sampling theorem that we would be, it would be guide us for the further evolutions of the signals and representation. So the part one of this theorem is performed in the transmitter section, and part two of the statement two is performed for the receiver section. Okay, and for a signal having the bandwidth, it is a band limited in the bandwidth of W hertz. So the sampling rate of twice of W samples per second is called the Nyquist rate, and its reciprocal would be called as a Nyquist interval. Okay, and we can also apply the proof of this in the next lecture. Actually the time is less, but you can draw this diagram till there is some time is remaining, and on the basis of this diagram I would be tell you how to do the sampling and what are the some mathematical. In this case we have to be define this sampled signal with the help of the mathematical equations. So here we are using the time domain representation, and we have to be also converted into the frequency domain. So we are going to apply the Fourier transform here. So I hope all of you have learned this in the signal systems. So applied or just take a revision of that Fourier transform. So we are going to use in the representation of this sampling theorem. Okay. Now, anyone has any question or query regarding the topic we have discussed today? You can ask your questions. Participants are 50 and attendance 44. Okay, thank you for attending the lecture today. So in the next lecture, we would be elaborate the concept of sampling theorem.